Alrighty, what's going on, guys? We're gonna start going over how to do Lab 3. So, a few bookkeeping things first. One, hope you all had a very good spring break. Hopefully, it was safe, responsible, and you made a bunch of good memories. So, make sure to inform me next time we meet. Want to hear what you guys did. I know a lot of you studied and was working on the report diligently. Proud of you. Good job for doing that. Hopefully you took some time for yourself to, finally relax. Another thing too, I am completely sorry for the delay of putting this out. I know that I said that I would get this out like almost a week ago, I think. This go around, my advisor really wanted me to do a lot of research. Since spring break, there's no classes. I really wanted to hunker down and get some stuff done. So, just in case you don't, or if you think I'm a liar, here's like some stuff that I've been working on. So, if you ever want to talk about this, by all means, we can. And also, if you want to get involved in some research, by all means, speak to me either after class, come by my lab, email me, reach out. Maybe I can get you started in our lab, or I know some professors that might be looking for something. So, just let me know. What else? I don't know if you might occasionally hear a squeaking in the background or if my dogs bark. Hopefully I can pause it in time. But you might hear some movement in the background, little steps here and there. So, sorry for that. Alright, bookkeeping's done. Let's get into it. So, if you guys remember, we did the Venturi Effect. Basically, we're looking at how a Venturi nozzle right here, basically you have something that chokes down. You have high pressure, goes to low pressure, goes to high pressure. Alternatively, another way you can look at it is you have low velocity, high velocity, low velocity. We're basically seeing the effects of what happens when you do that. Also, total energy loss. So if you guys don't remember from your lab manuals, this is what that looks like. Oh, also, short-term memory. I'm not sure if I just remembered to say this, but my mic, I don't know what's going on, but I sound like like I'm doing a pilot voiceover over the intercom. I don't know how to fix that, so please bear with me. I am sorry for that. But anyways, so here's the Venturi effects, but we have some issues, right? So one thing to know about the Venturi effect, using the Bernoulli's principle in particular, we could see here, right? If you have absolutely no frictional losses, you can, in essence, figure out what the velocity is at different cross sections. If you have a singular pipe, you can use the flow rate equation here. So velocity at one point is just a ratio of the areas to the velocity at a different point. Bernoulli equation, right? Pressure in one area, pressure to another. You have your static head, you have your dynamic head. All together, that is your total pressure or total energy. But you'll see here with the Venturi effect and the Venturi nozzle, you have a pressure loss that happens. So real quick, here's analog, right? You guys might have done this in Physics 1, where you have a block on a slanted surface, it slides down. You can also do this with a roller coaster. It starts at the top motionless as zero kinetic energy because its velocity is zero, but it has maximum potential energy. As it slides down, all that potential energy turns to kinetic energy. However, if it's a completely conserved system, the total energy is constant, right? Well, if you have some roughness for whatever reason, or in this case going across a bunch of barbed wire, apparently, you'll see here that while the potential energy decreases, like it normally would, the kinetic energy doesn't get fully recovered. There is some loss, and that's just due to friction. So I'll show you in your data analysis where you can see that, but just know that will happen. This is an unavoidable consequence of reality, specifically when you have, this is the diverging configuration, but anytime you open up, so you have a region of low pressure to high pressure where the flow has to slow down. It has to slow down somehow, and you'll typically have some turbulence start to form in the opening. So, or if you see right here, the fact that it has to very abruptly slow down in this corner will cause some backflow and that's where you will get some frictional losses. So what are some applications of this? A lot of people mention carburetors. Yeah, basically. Because you have a Venturi effect here, you have high pressure, and then because you choke it down here, you have low pressure region, because air is moving fast here. Because you have low pressure, high pressure in this fuel tank, you will draw in fluid into your air, and that goes to the combustion chamber. Combustion happens, that's how you power an engine. Same thing happens with like perfume bottles. When you squeeze that little bulb at the top, it forces air over the tank itself. Very long story short, causes a region of low pressure, sucks up fluid, and then it gets aerosolized. You can also see the Venturi valve or Venturi tubes in aviation. I'm going to be quite honest with you. This is way outside my pay grade or understanding of the class, but just to understand that Venturi tubes are Venturi valves, Venturi tubes. This effect is really good at figuring out certain flow speeds and fluid dynamics, right? One thing I want you to do in your lab report, especially in the introduction, I want you to explain the Venturi effect like I'm essentially a 5-year-old, right? I want you to don't just say like, oh, using the Bernoulli equation, it predicts this. Maybe just go a little step further and explain how. So for instance, when you go from a region of high pressure to low pressure, the velocity increases, right? That's something important. Dynamic pressure and static pressure, quickly explain what those are. Added together, that gives you the total pressure. The pressure is related to the total energy of the system. Total energy of the system can be measured using a pitot tube, which completely brings the flow speed to an abrupt stop, and that's how you read it using a manometer, right? All right, so I think that's as far as I want to go with theory, so actually let's start getting into your data analysis. So, data analysis. Let's start up at the top. So, here's trial 1. This is for the converging section. You'll have your volumetric flow, or your volume that you've collected. So in this case, I collected it for 1 liter, and then you have your time. Do some quick math. Note you're going to have to convert liters to meters cubed, but that'll give you your volumetric flow rate. Make sure you take an average of it, and you don't have to do this, but I would recommend taking the standard deviation to do that. It's equal STDEV, STDEV. You just select all these data points, and this will essentially tell you what kind of spread you have among your data. So when you plot your data, as I'll show you later, your data looks kind of off, like it's not following predictions. Looking at the standard deviation of your collected experimental data will kind of give you insight into how things are operating, right? So, looking into here, you have your taps, your distance to ducts. The only real thing that changed would be your static head, right? That's the main thing you measured. For trial 1, you also measured your total head, and you went through and essentially did that for all 6 trials. First 3 trials, those would be your convergent configurations. Trials 4 through 6, those would be your divergent configurations, right? Note that in your convergent divergent, you'll have your fastest speed, and then you'll have your slowest speed. That can be seen in velocity measurements. So make sure you take note of which ones are the fastest and lowest. So let's look at how we want to crunch these numbers. So let's just real quick look at the equations that we're going to be using. So our ideal flow rate is given by equation 6, right? In case you can't see that, let me just blow it up a little bit. Nope, that is not how you blow it up. There you go. So you can see here, your ideal flow rate is essentially just a rearrangement of the Bernoulli equation and the flow rate equation. You can rearrange to find your V1, right? and then multiplied by the area of the entrance. That will give you A1, multiply them together, that gives you your volumetric flow rate. So you can see here the main things that we're looking at are the head difference and your the area ratio, right? Those are the main things that are a part that we're going to be analyzing. Real quick, you theoretically can measure at any point in your Venturi tube. However, some points are better to get measurements from for different reasons. So you will notice that, hint, hint, this is a part of your discussion questions. Which ones do you want to measure? Which would give you the best results? Well, for one thing, you want whatever measurements will give you the biggest difference. And it's better to measure locations that are kind of far apart from each other. What do I mean by that? Well, let's go here. Here's the convergent and divergent configurations. You'll see here, you could do H1 and this would be H2. You can use those measurements. In fact, in one of the discussion questions, you're going to plot essentially what the flow rate looks like across this entire region. But you'll notice A, 1 and 5 are pretty far apart. In the divergent case, it's 1 and 2. And then B, you'll notice the pressure changes at the chokes. So for convergent, it's 1 and 5. You could see the head loss here, right? And to prove it, in the divergent case, it's 1 and 2. You can see that's the greatest difference that you get, right? So you might also have a question of, well, why can't I use, for the divergent case, 1 and 3 or 1 and 4? That's like further far apart in distance, right? Shouldn't that give me something better? If it was completely conserved, yes. It wouldn't really matter. However, let's look at, this will kind of answer the question with the question. So question 1 basically asks you to plot the total head for only the convergent case, right? And so that's exactly what I did. This is just the total head over the distance from station 1. So specifically, if I check here, all I did was took the total head measurement, applied this on the Y, and then distanced into the duct in millimeters. And we see that it starts to decrease. So we have an energy loss. So if I'm trying to show, hey, what's the best ideal case? I probably want to pick a point that's furthest from my first value. In this case, it's 1 and 2. But also, I'm not trying to pick up those extra losses that might give a different picture. Biggest thing though, in the convergent case, you want to choose 1 and 5 because they're pretty far apart distance-wise, so you can actually see some noticeable pressure differences. And then in the divergent case, you want, before you have all your energy losses for the ideal case, you probably want to get something right as that's starting to happen. So that's why you choose 1 and 2. Probably didn't the best way, or wasn't the best explanation. Email me if you want me to go more in depth about that. But yeah, so there's that. So anyways, we answered question 1. Let's quickly look at question 2. So question 2 for station n equals 5. So basically the choke. Plot the measured values of H1 minus H5. So this is the head difference from the start to the choke versus the flow rates. So we'll have 3 values of our experimental flow rates and then our ideal flow rates for each trial. According to equation 6, which is valid for frictional flow, Q ideal is proportional to this equation. I showed you that in class. Essentially, the thing that's out front is 2g divided by v1 squared. So that's just some proportionality constant. Consequently, the pressure difference versus Q ideal would be a straight line through the origin. Right? However, the points in that plot, as represented by the pairs of blank and Q experimental, may not lie on a straight line due to inevitable friction effects. So let's see if that happens. So we're going to go here. I made this column where it's just your theoretical flow rates. You could do this throughout the entire pipe. This equation right here is simply this, where H choke, and I should call this also H choke, will be 0.5 tap 5 for the convergent case, and it will be 2 for the divergent case, right? So for now, all we're doing is looking at our theoretical flow rates, and then your experimental flow rate, this would be experimental, okay? So there you go, to which it now overflowed. That's nice. All right, there you go. All right, cool. So basically, you have 1, 2, 3 trials. So for the convergent case, so what does that look like? Well, we can see here, all I plotted were, this is something I'd also recommend you do. Make a completely separate table where you have the square root h1 minus h5, just make that one column right here. And you can pull these values. So here's trial 1. Trial 1 for me in this case was my fastest measurement, right? So if you're looking at the speed right here, this is 0.27. For trial 2, it was 0.196. And then for trial 3, it was 0.087. So you can see here, I specifically labeled them. Sorry. T1 fast, trial 2 medium, T3 slow. So I have here my experimental flow rates for all those. So this is from the average. And I should be a good scientist and actually label them. And make sure when you're doing your lab reports, you have all columns labeled properly. There's a square root of a head difference, so your units will be square root of meters. And then your theoretical flow rate evaluated at your chokes. So for example, T1 fast, trial 1 fast. Okay, it'd be, here's tap 2, tap 3, tap 4, tap 5. So I would use this guy, right? So you can see here, that goes right there. Don't worry about the C column and delta C column just yet. Right now, we are just plotting this. So when you plot it, you'll have 2 separate lines. You'll have your theoretical equation. So if I show you real quick, here is select data. My experimental, my x values are the square root h1 minus h5. And then my y values are the experimental. And again, for theoretical, it is h1 minus h5. And then I have Q theory, right? Because it's theoretical, I would highly recommend throwing in some trend lines. This is the one time you can use linear trend lines, and I won't say something and be super angry. Just kidding, I'm not angry. I'm never angry at you guys, most of the time. Anyways, you can see here, 9 to 10 minus 20, that's basically 0. So you can see here that the theoretical line does go to the origin. Something you should do, by the way, is these are measured experimental points. So just leave them as points. If you don't remember how to do that, double click the white space out here to bring up this formatting box, and then you just click on one of your lines. If you don't see, because it says trend line here, just go to experimental, series experimental, and now you can, if you want your line or your markers look different, here I'll make them, I don't know, diamonds. Remove the lines. Now there's no line. You can also remove the lines or the markers from your theory. So that's how you do that. They're going to do that for the convergent case. You do it once again for the divergent case. Right? So this is what they both look like. You can see that it's pretty close. They're pretty close, but we do have some divergence. Also, sorry if you can hear my dog whining. He shoved a squeaky underneath the couch, and I'm refusing to get it to him. You don't want to enable that behavior. Anyways, so that answers 2 and 3. So, equation 4. This is where it gets interesting. This ratio, C, is also known as, I am forgetting. It's not displacement. Oh my god. I'm going to remember it as we're covering it. Anyways, it's basically a ratio that lets you know discharge ratio. I am a great TA. It's a ratio that basically tells you, hey, how far are you from theory? Or another way to look at it, how bad is your frictional losses? The closer to 1 you are, or unity, that basically tells you you have minimized frictional losses. You are very close to theory. Bernoulli's equation holds up really, really well. So it's really easy. All you have, once again, you have 3 experimental, 3 theoretical flow rates. The ratio is just experimental divided by theory, and all you're going to do is just plot them, right? You're going to plot them, so for 4, let me show you here. You can see 4, all I did was plotted on the x-axis is Q experimental, so in case you don't believe me for some weird reason, let me just show you. I have selected your experimental is going to be your x-axis, and then your y-axis is C, right? And you're going to do that again for the divergent case. Great. Now, you might notice it looks like your convergent case starts to go down. Maybe your divergent case is low, slow, whatever reason. Remember how I told you to write down the standard deviation to see if your theory is bad or not? Because this might give you something misleading. Well, this is where that part comes in. So these are called error bars. They basically tell you how bad, or not how bad, how uncertain your measurements are. So for example, let's look at the flow rate for trial 2. You can see I have a pretty large spread over my data. I know some of you have large spreads over your data. That's not wrong, that's not incorrect, but you should at least take note of it. So one way you can take note of it, this is bordering on beyond the scope of the class, but essentially if you want to figure out your uncertainty in C, your discharge coefficient, essentially you do something called adding in quadrature. Very long story short, this is how you calculate it, right? So 1 over your theoretical flow rate times your uncertainty or your standard deviation for that trial of your experimental flow rate. So for example, here's delta C. So it is for trial 1, the uncertainty measurement of Q experimental times or divided by Q theoretical for T1. You do not have to do this. You do not have to do the delta C thing. I just threw up error bars here because it took me a long time to figure out why this isn't working. Because one thing to note, and you should definitely do this when you're answering your discussion question, it's good to have external resources. There's a discussion question that asks, hey, as you start getting faster and faster with your flow rate, so you're pushing more fluid through, it's going at higher velocities, does your flow rate start to approach unity? Now, it's kind of a leading question, which made me think yes. So I went on Engineering Toolbox, which you're going to go to this website a lot of times for many different things. Reynolds number is essentially, for our purposes, the higher the Reynolds number, the higher velocity. And as you can see, as it starts to speed up, it gets closer and closer to 1. So I thought my data should look like that. You can see the divergent, it does. Convergent, it kind of doesn't. Then I looked at the error bars for these and I realized, oh, okay, so my true value might be approaching 1. It might be very slight. It's just really hard to see. So yeah. By the way, if you ever wanted to add these error bars, here, I'll even show you how to do it. Click your line. So I want to add error bars to my divergent line. Go to add chart elements, error bars, doesn't matter. You can pick standard. We're going to get rid of the horizontal error bars. Click the vertical error bars. Go custom. Specify value. Delete what's there. And we are going to select just these. And bish bash bosh. Look at that. And there you go. So also have high error for the divergent case. That could be a lot of reasons. Maybe there was some trapped air in the fluid. since you're measuring the volume being collected, I noticed that some people's measurements were yo-yoing a little bit. That could be a whole litany of reasons, but it could just be errors in taking those measurements. It just maybe wasn't collecting in a steady state. So just make sure you talk about it. It's okay if it doesn't line up. Just know the faster and faster you go, you have a higher Reynolds number. If you don't remember, Reynolds number is a ratio where you worry about inertial effects over viscous effects. I think I spelled that right. So basically, your frictional losses start becoming less important than your inertial effects. So the fact that you're trying to ram it through small bodies, so backflow might become still an issue, but your viscous forces start becoming less and less important for higher Reynolds numbers. So for those who watch this, I'll just basically kind of let you know, you should start expecting this. Your data should start trending like this divergent case, closer to some value, which should be apparently obvious. Okay, so that's Q4. That's question 4. A lot goes into answering that equation. So let's go in and answer the last one, Q5. So Q5 basically wants you to test what equation 8 is. If you don't remember what equation 8 is, it is this ratio. Basically, you multiply it across, cancel out some areas. You should be left with the left-hand side of the equation is equal to the right-hand side of the equation if you have no frictional losses. If you have frictional losses, the left-hand side will not be equal to the right-hand side when you plot it. So if this side is equal to that side, your ratio should be 1, or you can think of it as 1 is equal to 1, or another way that you can think about it is x is equal to y, right? If x is equal to y, well, that's just a straight line with a slope of 45 degrees. How do you plot that? I'll let you know. I'll help you out. So let's go and immediately do that. So I have a column here, this little box. By the way, I have the ratio, or my Reynolds number. If you ever want to figure out what your Reynolds number is, I use this equation right here, where D1 is your entrance diameter. That's your characteristic length. Nu, this little v down here, Greek letter nu, is your kinematic viscosity. So to calculate it, do V1 times your diameter. You have to convert that because it's in millimeters. Divided by your kinematic viscosity, which is this value right there. You're going to be using, if you're not already, Reynolds number is going to become one of your life force extensions of you. Anyways, so I have here, I just plotted the left-hand side of equation 8. Here's, so basically this, and the right-hand side of equation 8. You'll notice here, left-hand side of equation 8, kind of can't do that, because it's going to be 0 is equal to 0. That's boring and trivial. So really, you don't need to plot that side of the equation. But all I did was just went through, bless you, that was my fiance, not a ghost, I promise, or a hallucination. Though if you do experience those, please talk to a medical professional or a psychiatrist. Anyways, you're going to go through and plot out using the values for each trial. Make sure you are familiar with your percent sign, or not percent, dollar sign. That locks in a cell, so you can reuse that without it like drifting out as you drag the formula down. And the right hand side, again, is just the area ratio squared minus 1. Also, I find it a lot more helpful if you use the power function. Not only is it more versatile, it keeps things a lot more tidy, so you can see the number that you're wanting to evaluate, and then any kind of power. So you can do 1/3, 1/5, 0.239, whatever you want. Just keeps things a lot more tidy. And then your ideal. What is your ideal? Well, I told you, x is equal to y. If this is your y, this is your x. So all you're going to do is just click and drag that down, right? Okay, so what does that look like? Let's go down. And this is the convergent configuration, right? When I think I actually narrowed this down. Here, let me check something. Reset. Yeah. So if x is equal to y, if you want to kind of see these data points a little bit, here you can see your 45-degree slope line passing through the origin. That's your ideal curve. You can just change this down to 10 if you want to see more data points. Heck, we can change it down to 6 if you want to see more data points. My convergent min and max were very close to each other. So what I did was I just changed the markers of these to one's a triangle, the other's a diamond, just so you could see it. You don't have to do that. Just make sure in your lab report you just write, hey, that they're overlapping, just so we know that you actually did plot them. And again, the convergent case, your choke happens at tap 5. The divergent happens at 2. So make sure you just write that accordingly. But you can see here, we do have a fair amount of, I don't want to say divergence again, but divergence of data from theory, right? So that's basically it. That's enough for the convergent case. And I did the exact same thing. Oh, yes. I did this for the maximum flow rate and then the minimum flow rate for the convergent case, right? So for the divergent case, you'll once again have maximum and you will have minimum, okay? Something interesting for the divergent case. You can see here if you just tried plotting, so I'll show you what I plotted for this. Select data. If I try doing the ideal, I jump from, well, it's actually down here, but I go, okay, here is my x values, and then here are my y values. If it's a smooth line, it's going to suddenly jump to a maximum and then go backwards, and that looks really weird. So you could do one of two things. You could just not plot that, and it might fix itself. Yeah, it'll fix itself. Or you can correct your orientation, right? So if you correct your orientation, it looks like that. So all I did was manually move it. I'm not gonna lie. You know what's gonna be way easier than doing this? Just delete those points. Just do this. Your life will be way easier. Less confusion. You might still need to flip some data points around. I don't think I flipped the data points around. Honestly, I take it back. Just correct the orientation. It'll be less confusing for you guys. So you should end up something that looks like this. And you can see that the divergent case, you have some pretty substantial deviations from theory, right? So let's think about why that could happen. I showed you in the theory section here. This would be for the divergent case, so the part that's nice and slopey. That happens afterwards. You have a lot of backflow up here. That could be an example, maybe. I tried looking online if the convergent case and divergent case, which one's better. And a lot of them I've seen this is kind of the standard configuration. One of the biggest things to note is that you want to expand gently, like this. Otherwise you will have greater frictional losses, which might also explain too, if you look at this case, the convergent doesn't seem to have as high of a performance as the divergent case. Okay. That basically does it for at least the first 5 discussion questions. What else is there? We have addressed this if you paid attention to my video. Same thing with this one. This one's kind of interesting. Assuming that a fluid particle moves from 1 to 6 along the center line of the Venturi tube, can you estimate, using the experimental data, what is the energy loss of the particle during that period? Okay. So what that means, and this is like, do you understand how total pressure works? Let's say we are far away from the walls, so we don't have to worry about, we have like turbulence and vortices occurring from the side, from expansion, what have you. All we do is move along the center, so we just focus on just the kinematic viscosity, right? So static head, let's say, should remain ideal from here to here. So let's say static head at 1 is equal to static head at 6. It should be, right? If this is equal to this, if we're looking at the total energy then, or if you want, I can open up Paint. Everyone loves 3D Paint. So we have, here is our point. Here's X. So this is point 1. This is 1, 2, 6. Our kinematic velocity or energy should look something like this. If we have no head loss, right? Well, I'm sorry. This should be like maybe the static head, right? Let's just say. However, we notice that our head loss, instead of being our static head, instead of being like that, it's more like this. So we have some head loss. So because we have lower potential energy now, seemingly afterwards, right? Our ratio went down. Our total energy ratio went down. You could then say, well, if I just am following, say, the velocity of that particle, well, it looks like the velocity went down, right? Which is kind of weird, because if you think about it, we should have the flow rate equation, V1 divided by A1. That should be equal to any part, any position, right? You should be able to follow this. And it kind of does, but there is less energy that it has. Something had to drop, and that was its static head. The potential energy went down, right? So, that essentially answers one of the hardest. There's a lot loaded into question 3 in the further discussion. And then would a different Venturi meter give the same values of C? That's pretty self-explanatory, because you graphed it. So I will let you answer that one. Please don't get that one wrong. You'll make me sad if you've watched this video. So anyways, that answers everything that I could think of. Of course, if you have more questions or something's not being plotted correctly, just shoot me an email. Once again, I am extremely sorry this video has gotten out so late. I, A, have been very busy over spring break, and B, I wanted to make sure that I checked up on a few things involving the theory and how to answer some of these equations to better suit your guys' learning. So anyways, I will catch you guys in lab this coming Tuesday. So, alright guys, I will see you then. Bye!